quick introduction in French. Donc, mon projet fait partie d'un projet plus large qui est le projet Doc 3D Printing, qui est un projet européen qui a rassemblé 14 doctorants dans différentes institutions et qui a été formé par 14 partenaires industriels et universitaires autour de la fabrication additive de céramique, donc du développement des matières premières au test des produits finis pour les secteurs de la santé et de l'espace. Et mon projet, plus particulièrement, s'articule autour du développement du procédé de stéréolithographie appliqué aux biocéramiques. Donc la stéréolithographie, c'est un procédé de fabrication additive, donc c'est-à-dire la fabrication d'objets en 3D, couche par couche. Donc c'est simplement comme avec une imprimante classique en 2D, sauf qu'on imprime des formes que l'on colle les unes aux autres jusqu'à obtenir un objet. Et application aux biocéramiques, les biocéramiques sont des matériaux qui font partie du domaine de la santé. Ce sont des matériaux qui sont compatibles avec le corps humain, c'est-à-dire qu'ils ne causent pas de réaction inflammatoire ou nocive pour le corps humain lorsqu'ils sont utilisés à son contact. So the idea of this project emerged when thinking about the additive manufacturing, which is a fast-growing technology that provides a fast prototyping, the possibility to produce objects with complex shapes, and a great adaptability. And we decided to combine that with the orthopedic, where the increase of the median age of the population and a lot of diseases or accidents cause a lot of damages on the human body, and therefore a crucial need for bone implants. And finally, there are the bioceramic material, which are biocompatible, so can be used in the human body. And all of that brought together gave us the idea of the additive manufacturing of bioceramic material, which could provide biocompatible implants adapted to each patient. So first of all, the additive manufacturing can be classified into 4 main categories, depending on the type of process and depending on how the layers are built. So there is the material extrusion, the material goes through a nozzle, the powder bed fusion, so it's a powder bed, and the powder is sintered or melted with an energy source, the material jetting or the binder jetting, where the binder is jetted on the material, and finally the photopolymerization technique, where the light is at the center of this additive manufacturing technique. And within the photopolymerization techniques, the stereolithography process provides a high resolution and a very smooth surface finish. Is it okay with the mic? Sorry. Sorry about that. So the stereolithography process uses suspensions as a feedstock. So a suspension is made of the photosensitive resin, which is composed of different monomer and the photoinitiator and is at the center of the photopolymerization, mixed with the bioceramic powder, which is the powder that we want to print. There is 2 different types of stereolithography process, the ones using lasers as the light source and the one that are using a dynamic light projector as the light source, these ones enabling to cure the whole layer at once. The machine that was used for this project is the ADMAFlex 130 that was provided by a company called Admatec, and that uses the DLP technology that provides light at 405 nanometer. So basically, the DLP is below here, and this technology combines the stereolithography process with a tape casting process. So the material is casted onto a plastic film, thanks to a doctor blade, and then illuminated from below with the DLP. So the process is as follows. As I mentioned, the suspension is casted onto the plastic film, illuminated from below, which leads to its photopolymerization, bringing us the green part, where the bioceramic powder is trapped inside the photopolymerized resin. This part has then to go through the debinding cycle in order to remove the binder, and the sintering cycle in order to densify the ceramic powder and obtain the final ceramic part. At the moment, the production of densified and defect-free bioceramic with the SLA process is very difficult because there is a lot of defects and cracks that can appear during the different steps of the process, especially during the printing and the binding and sintering steps. However, moreover, the stereolithography process was mostly used with alumina and zirconia when I started this PhD, but there has been a lot of improvement in the last 3 years, and there is, for example, 2 different companies that are now commercializing suspensions with TCP material or hydroxyapatite material, so Lithos and Admatec. Finally, most papers in the literature don't detail the whole composition of the resin, so it's difficult to adapt this printing process to a specific powder because you usually don't get the resin and the powder separate. So the objective of this work was to use the beta-TCP powder in a suspension for application as bioimplants and to prepare a homemade resin that can be tailored in order to improve the printing and the binding steps, and that can also be used with the specific beta-TCP powder. Finally, the optimization of the process has to be made in accordance with the composition of the suspension and the light parameters on the equipment. The binding and the sintering step had to be adapted. So there is a lot of requirement that goes with this process. First, the suspension has to have a sure thinning behavior with a low viscosity, an adequate reactivity, and a high solid load. And as I mentioned, the printing parameters have to be adapted to the composition of the suspension. The resin has to provide a solid polymer network because we want to be able to handle the grain parts, and has also to be easy to remove in order to avoid the appearance of cracks during the debinding. Finally, the powder has to have good sintering properties, and in order to obtain a final ceramic part with a high density that is defect-free and that has suitable mechanical and biological properties. So the first step was the understanding and the optimization of the process was to start with the synthesis of the powder and its characterization. So the powder was synthesized here in the LMCPA with the help of Nicolas Sommers, and it was synthesized through aqueous precipitation in a reactor, and then went through drying and calcination at 850 degrees Celsius during 3 hours, giving the beta-TCP raw powder with a density of 3.28 grams per centimeter square. I did some grain size analysis of this powder, and I obtained a very wide grain size distribution. And I also did some XRD analysis on the powder in order to attest its composition. And I realized that two phases were present. The beta-TCP phase is mostly present in the powder, but there is also a slightly bit of hydroxyapatite, which was not a problem for the application targeted. So the next step was the study of the resin. So the resin is, as I mentioned, at the center of the stereolithography process because of the photopolymerization reaction. So the resin is composed of a photoinitiator and a monomer. In the literature, most of the monomers used in the SLA process are acrylates. And basically, the photoinitiator interacts with the light and gives two radical photoinitiators that are then able to react with the acrylate monomer, breaking the carbon-carbon double bond into a single bond and enabling the monomer itself to react with another monomer, therefore giving the 3D photopolymer network. So, thanks to for a literature study, I did the first selection of the component of the resin. So the photoinitiator have to be chosen considering the wavelength of the light source, and I decided to choose 4 different photoinitiators: the ERGA-Curie, the PTQ, the BAPO, and the TPO, in accordance with what I found in the literature and that what was used with bioceramic material. And I also selected 6 different acrylates with different functionalities. So G-acrylate, a metacrylate, a 3-metacrylate. So these are the 3 functionalities. Another G-acrylate, another triacrylate. I did some first photopolymerization preliminary tests, mixing all of the monomers with 0.1 weight% of photoinitiator. I placed the monomer on the plastic film, illuminated them with the DLP of the ADMAFlex machine, and evaluated the produced sample. So, what first appears here is that the ERGA-Curie and the PTQ did not give the best results in terms of photopolymerization with the monomer used. So the TPO and the BAPO enable the photopolymerization of several monomers and are therefore the most suitable photoinitiator to be used at 4 or 5 nanometer. Also, what we can see here is that the monomer have different reactivity, seems to have different reactivity. The TGDA, which provided a strong photopolymerization with a solid and thick illuminated sample, seems to have a high reactivity, the TMETA as well, whereas the HEA-MA, which did not polymerize with any of the photoinitiators, seems to have not a very good reactivity with these printing parameters. But these were just some assumptions at first. So, in the literature, Actually, the TPO and the BAPO are preferred with the DLP machine. So this was consistent with the preliminary tests. I added to that some rheological characterization of the monomers because the viscosity can also impact the reactivity of the monomers and the viscosity of the suspension. And as the goal is to have a good reactivity and a low viscosity of the suspension, I realized that the TMET-PA and the PEGDA had too high viscosity. So I decided not to pursue the experiment with these two monomers, and I finally selected only 4 different monomers and one photoinitiator that worked, the TPO. I also realized that in most of the composition of the resin that are presented in the literature, the acrylate monomers are not used on their own. They're often used with an additive that can improve the reactivity, the cleaning, and the debinding step. So I selected the polyethylene glycol 200 for this purpose. So I did a better evaluation of the reactivity. So basically, I measured the mass of a liquid sample and I placed it on a plastic film, illuminated it from below with the DLP of the machine, and measured the mass of the photopolymerized sample, calculating the percentage of photopolymerized mass. The results were these ones. So the TGDA and the HDDA provided photopolymerized mass around 60–65%. The TTA seemed to provide the higher photopolymerized mass with 78%. However, I also measured the hardness of the photopolymerized sample, and I realized that the sample produced with the TTA were too soft to be tested. So the TGDA and the HDDA provided a solid photopolymer network, whereas the TTA had the highest photopolymerized mass, but provided a soft photopolymer network. I also did another experiment where I mixed the TGDA and the HDDA alone, and then where I added some polyethylene glycol 200. And what I obtained was that the addition of polyethylene glycol 200 seemed to increase the photopolymerized mass, the percentage of polymerized mass. However, it is difficult to draw conclusion with this experiment because the reactivity is not exactly equal to the photopolymerized mass. So I added some IR measurements to evaluate the bond conversion and to understand better what happens during the photopolymerization reaction. So I did the IR measurement on 3 of the monomers, the TTA, the TGDA, and the HDDA. So I did some IR spectrum before the photopolymerization and after the photopolymerization. And I evaluated the peak area on 2 bonds, the double bond CO, which was used as a reference because it is not impacted by the reaction of photopolymerization, and the double bond carbon-carbon, which is impacted because it is converted into a single bond. And thanks to the calculation I found in an article, I was able to calculate the conversion rate of each of the monomers. And what appears here is that the TGDA and the HDDA are actually the monomers with the highest conversion rate, meaning that they are the monomers with the highest reactivity compared to the TTA. So how can we explain that? Well, a high reactivity can be linked with the entrampment of photoinitiator radicals during the photopolymerization reaction if this reaction happens too quickly. So this can explain the lower photopolymerized mass obtained in the first test, whereas the average reactivity that was shown for the TTA in the IR measurements leads to a slower photopolymerization reaction, which can explain the higher photopolymerized mass in the first test because there were not any entrapment of the radicals of the photoinitiator. However, what about the polyethylene glycol 200? Well, I measured the viscosity of the polyethylene glycol 200 and I realized that its viscosity was above the viscosity of all the other monomers, meaning that the increase of viscosity of the resin will decrease its reactivity and therefore slow down the reaction, avoiding the entrapment of photoinitiator radicals in the network and therefore increasing the photopolymerized mass. So that was how I was able to explain the results obtained during the first photopolymerization tests. So finally, that brought me to my final selection of the monomers that were going to compose the different resin. I chose the HDDA for its high reactivity and low viscosity, the TGDA for its high reactivity and average viscosity. I also decided to pursue the experiment with the HEMA, even though it has a very low reactivity, but also because it has a very low viscosity. And I decided to keep the polyethylene glycol 200 that can slow down the photopolymerization and also act as a plastifying agent. All of that was made in order to obtain printable suspension with low viscosity, high reactivity, and a solid photopolymer network to handle the green parts. So the next step was the mixing process. I actually struggled a little bit with the mixing process because at first I was using a 3D rotary mixer, and I had to place the suspension that went through the 3D rotary mixer through a free roll mill after that. So there were a lot of loss of matter in the process. So then I went to another technology, which is the speed mixer, that provides a dual centrifugation force, and that is easy and very fast. So I was able to obtain smooth and homogeneous suspension in less than 15 minutes, and also using only one container, so avoiding the transfer of the suspension and avoiding the mass loss during the process. But the powder has also to be coated with a dispersant in order to be mixed with the resin, because the powder mixed with the resin on its own agglomerates and creates a suspension, a non-homogeneous suspension with a shear thickening behavior. So I choose the Zelec P312, which is a phosphoric ester, as a dispersant, and I mixed it with my powder in ethanol with a grinding media. All of that went through a 3D rotational mixer. Then the beads were filtrated and the ethanol eliminated, leading to the obtention of the ceramic powder coated with a dispersant. How does the dispersant work? Well, the dispersant absorbs around the β-TCP particles, providing charge on its surfaces and providing electrostatic repulsion. Also, this dispersant can also provide a semi-steric effect, but not a complete steric effect, because the molecule of this dispersant particularly are very short. So all of that was made in order to avoid powder agglomeration. I tested 3 different rates of dispersants in the mixture, 0.35 weight percent, 0.5, and 0.7, and I measured the rheological behavior of each of the suspension at 2 different shear rates, 100 reciprocal second and 200 reciprocal second. And here it appears that the suspension made with 0.5 weight percent of dispersants were the one providing the lowest viscosity, which was what I was looking for. So this was the optimum dispersion rate to be used for my following experiments. I did the granulometry analysis of the coated powder in order to compare it to the raw powder, because the grinding media also enables to deagglomerate the powder. And I, in fact, realized that there is a thinner grain size distribution of the powder that can help with the sintering process. So I decided to pursue the experiment with this coated powder. The next step was to evaluate the influence of the resin composition on the properties of the suspension and the printed parts. So with the 4 monomers that I selected, I varied the composition using always the same amount of powder, which was 48 volume percent of β-TCP powder. So I first evaluated the rheological behavior of all of the produced suspension, and I realized that all of the suspension presented a shear thinning behavior, meaning that the viscosity decreases with the increase of the shear rates. However, Admatec recommends the use of viscosity below 10,000 millipascal second to be suitable for the use of the machine. So only 3 of the suspension had a viscosity adapted to the printing process, even in the low shear rates. The suspension composition 6, 7, and 8. So when I realized that, I started to make some assumption on what monomers could work and which monomer would work and which wouldn't work. So it appears that only the composition prepared with 45% of TGDA or less had a suitable rheological behavior. The use of HEMA that can actually decrease the viscosity of the resin didn't seem to have a direct impact on the viscosity of the suspension. At least 15% of polyethylene glycol 200 seemed to be needed. And finally, as I mentioned, there were no direct correlation between the resin viscosity and the suspension viscosity. So I pursued the experiment with the printing tests. I selected 2 different designs, a cube with holes and pellets with a diameter of 12 millimeters. I printed 5 samples of each design and evaluated them. I built the binding and sintering cycle based on TGA analysis and dynamic analysis. So first, I observed the printed pellets with a 3D microscope. And what we can see here quickly is that not all the suspension lead to the same sample. So the sample 1, 2, 3 and 7 presented big cracks and delamination, whereas the sample 4, 5, 6, and 8 appeared to be defect-free at this, with this experiment. So here, all of the suspension prepared with 60% of TGDA presented cracks and delamination, but the suspension were also the ones with the highest viscosity. So this defect could have actually appeared during the printing process. However, the only sample that it wasn't able to explain here was the sample number 5, because it was printed with a suspension with a very high viscosity and had no defects here. So I decided to do more experiments, and I observed the sample with SEM analysis. So I did this SEM analysis on the cubes with holes. Here you can see the same defect on the sample 1, 2, and 3 that appeared on the pellets. So there is cracks and big delamination. Also on the sample 7, there is cracks and a lot of defects. And the only difference that was observable compared to the previous test were for the sample 4 and 5. The sample 4 and 5 appeared to be defectless, but here there is actually defects on the surface, and there is also a lack of precision in the structure because this is supposed to be a square shape. So the suspension composition 4 and 5 actually did not provide the best quality of sample. So this made me wonder, do I need at least 40% of HTDA to manufacture a suspension that is going to be printable? And is the use of HEMA really important? Because it did not seem to improve the suspension I prepared with this monomer. So finally, the suspension 6 and 8 were the one providing the best sample in all of the experiments. So here there is better precision compared to the other sample, and there is only a few defects on their surface with very small delaminations. So I added to that some density measurements done by the Archimedes method. And here the suspension composition 4, 5, 6, and 8 were the one providing the sample with the highest densities, with a relative density above 98%. So combining all of these results together, so the density measurements, the microscopic measurement, and the SEM observation, it appeared that the suspension 6 and 8 were the one providing the best parts with only a few defects and a high density. So these were the composition that I selected to pursue the experiment, that were the optimum composition to be printed with the powder I used. So I evaluated then the influence of the solid loading. So I chose one of the optimum resin, and I tried 3 different solid loading. So, and I did some rheological analysis. What appears here is that the increase of the solid loading obviously increases the viscosity, and the suspension prepared with 73.3 weight% of powder actually has a viscosity that is above the limits recommended by Admatec. However, all of the suspension were possible to print, and so I printed this time some square-shaped samples. And I did some density measurement and mechanical analysis with the 3-point bending tests. What appears here is that the increase of the beta-TCP solid loading seems to lead to an increase of the relative density and an increase to the bending strength, but up to a maximum. So here it is difficult to draw a really precise conclusion due to the error of measurement. However, the tendency that is observable with the density measurement is the same that is observable with the mechanical analysis. So we can assume that the increase of the solid loading provides a higher density and improves the mechanical properties, but up to a maximum. And this could be explained by the fact that the suspension prepared with the highest amount of powder has a very high viscosity, so that can cause defects appearing during the printing process. I did some SGM observation to pursue the experiments, and here it appears that it's consistent with the results that were observed during the density measurement and the mechanical analysis. On the sample prepared with the least amount of powder, there is a lot of defects, a lot of delamination, and some residual porosity. On the sample prepared with the intermediate amount of powder, there is no visible defect. However, there is still some inside porosity in the sample. And for the sample prepared with the highest amount of powder, there is a delamination. So the next step was to evaluate the influence of the light parameter, choosing again the best resin. And I decided to stay with 48 volume percent of beta-TCP powder to pursue the experiment. So I printed again the cube with holes, this time with the goal to measure the precision of the size of the holes in the printed parts. So I tried different combination of light power and exposure time. So first decreasing the light power with the same exposure time, then decreasing the exposure time, and again decreasing the light power. And then I tried a very long exposure time with a very low light power in order to see the influence of the energy dose on the printed samples. So what appears here for the first sample that were observed with a microscope is that the measurements made on the top surface, so the measurement of the size of the hole, are not the same that the ones made on the side surface. So there is different precision due to the printing process on the top surface and on the side surface. And actually the precision on the side surface is quite good. So I decided only to evaluate the top surfaces of all the samples. So here, for the sample A, for example, the pores on the top surface only have a 1.9 millimeter length, whereas whereas the original design pore size is 2.4 millimeter. So this was lower than expected. And actually, the same happened for sample B, that was manufactured with the lowest light power. And sample C was a little bit better, but still a bit far from the original design. However, the decrease of light power seems to increase the precision. So when I decreased both the light power and the exposure time, I finally managed to obtain sample F and G. So here, that were the one with the pore size on the top surface that were closer to the original 3D design. So, and when I evaluated the last sample, that was sample number H, with a very long exposure time but a very low light power, it was not better than the other samples. So here, the long exposure time with a short light power doesn't work. The energy dose seems to be too high to be printed with the composition of my suspension. So actually, the best energy dose were 25% of light power combined with 500 milliseconds, or 20% of light power combined with 500 milliseconds of exposure time. That's enabled to have the best printing precision. I also evaluated the slice thickness. So the slice thickness is how you decide to cut your design when you implement it in the machine. And I tried 3 different slice thickness, 20 micron, 30 micron, and 40 micron. Here it appears on the SEM observation that the surface of the sample printed with 20 micron seems to be rougher than the surface of the sample printed with 30 micron and 40 micron. So there is more defects here on this surface. And this was confirmed with the roughness measurements. Actually, the surface of the sample printed with 20 micron had a higher roughness than the sample printed with 30 micron and 40 micron. So the slice thickness can influence the roughness of the sample and therefore the appearance of defects on the sample and the decrease in mechanical properties. So finally, the conclusion of this understanding and first optimization of the process, was that it was possible to manufacture a homemade resin with 3 different monomers, the TGDA, the HDDA, and the polyethylene glycol 200. And I was able to obtain a suspension with a shear thinning behavior and a low viscosity. Moreover, using 72.7 weight percent of beta-TCP powder enabled to increase the density of the printed sample and their mechanical properties, and the light parameter, so the light power, the exposure time, were adapted to the composition of the suspension, and also the layer thickness could be adapted to the composition of the suspension. And all of that enabled the printing of dense parts with density above 98%, with only a few delamination and an adequate precision. So the next step was to adapt this optimized composition to complex shape, because the goal is to print bone implants, and the bones are not just rectangles. They have porosity gradient and they have different structure. So the original design chosen here was a foam with random pores and a thick base at the bottom without any pores. And here it appears that it was possible with the optimized composition to print such a part. So here the base was actually dense and the different porosity could be printed and the part could be cleaned could be cleaned easily. However, there is still some work to do on these parts because there is still some cracks and delamination that seems to appear on the samples. But this result is very encouraging for the future development of this process. The next step was then the biological characterization, again, because the goal of this optimization was to use the sample for burning plants. So I chose two different designs, a β-TCP pellet with pores and a β-TCP pellet without pores. And I printed them with the optimized composition and the optimized machine parameters. And I used alumina samples as a reference material because of their known biological properties. So I used two different types of cell, MC3T3, and row 264.7 cell, which are pre-osteoblast and pre-osteoclasts. And first, I observe, the repartition of the cells on the surface of the sample was observed with a microscope in order to see if the cells were staying on the sample. So the experiments were made with toluene in blue, which is colored in blue in the presence of cells. So this confirms that the cells stay at the surface of the sample. And here in the samples with pore, we can even see that the cell migrated inside the pores. So then the next step was to evaluate the cytotoxicity of the sample. So on all the experiments, there is some samples, reference samples, and some samples that are marked with RONCO. So this is a transcription factor that is designed to reproduce in vitro the cell differentiation environment. However, it does not impact the cytotoxicity measurements or the cell proliferation measurements. So here, the LDH activity was measured after 2 days of culture and after 5 days of culture. And the LDH is the enzyme liberated during the cell lysis, the death of the cells. And it appears that there is no significant difference after 2 days and after 5 days between the alumina samples and the β-TCP samples. So the printed sample appear to be non-cytotoxic because the alumina samples are known to be non-cytotoxic. The second step was to evaluate the cellular proliferation on the sample. So here again, there appear to be no differences between the cellular proliferation after 2 days and after 5 days between the alumina samples and the β-TCP samples, except here where the cell proliferation is even higher on the samples produced with β-TCP on the sample printed with pores. So there is almost no significant difference. So the printed samples seem to enable the cellular proliferation at least as much as good as the sample produced with alumina powder. The same results were obtained with the MC3T3 cells because the first one were done with the pre-osteoclast. And here there were, again, no difference between the alumina samples and the β-TCP samples with and without pore. So again, this cell could proliferate on the printed sample with the optimum composition. The next step was the evaluation of the cellular differentiation. So I only presented one of the 5 tests that have been done because actually 4 of the 5 tests gave the same results. So this is here where the RONCO is useful to evaluate the cellular differentiation. So the acid phosphatase activity is measured, which is a differentiation marker into osteoclasts. So the goal is here to see if the pre-osteoclasts were able to evolve into osteoclasts. And it appears that after 2 days, there is a slight increase in the acid phosphatase activity for the β-TCP with pore sample, and the same result is visible after 5 days. Even if here the difference is non-significant, it appears that there is a tendency that the acid phosphatase activity will increase with the production of β-TCP samples. So this means that the β-TCP sample enables the cellular differentiation better than the alumina sample. So in conclusion, the β-TCP sample printed with the homemade resin and the optimized SLA process were not cytotoxic. They enable the cellular proliferation, and they also enable the cellular differentiation better than the alumina samples, which means that, which confirms the bioactive properties of the β-TCP, because the alumina is bioinert, so it doesn't enable the cellular differentiation, whereas the β-TCP samples enable the cellular differentiation. So the final, however, even if the process was optimized, there is still some remaining challenges because the thermal debinding and sintering processes were very long, 23 hours and 40 minutes. So the idea was to try and use two different new technology, the CO2 supercritical debinding and the microwave debinding and sintering, and to see if this technology could be used with the SLA process. So firstly, the sample were printed with the optimized composition and the optimized light parameters and went through different debinding steps. So this sample went through the supercritical CO2 debinding and then the thermal sintering. This sample went through the thermal sintering, thermal debinding and thermal sintering, and this sample had no debinding at all. So it appears that the sample that went through the thermal debinding and sintering cycle had no defect, whereas there is delaminations on the sample that went through the supercritical CO2 debinding. However, it seems that there is less delamination when the supercritical CO2 is used compared than when no debinding at all is used. So the supercritical CO2 could help to ease the debinding, but cannot be used on its own. So the idea was to combine it with a microwave sintering and debinding steps. So basically the sample is placed inside a microwave generator, and this microwave enables a volumetric heating of the sample that can reduce the appearance of defects during the debinding and sintering step. And it was possible to implement a cycle of a duration of 90 minutes and 25 seconds, which could enable to gain a lot of time in the production of these parts. So again, 3 different samples were printed, one that only went through the microwave debinding and sintering, one that went through the microwave debinding and sintering, but also a pre-debinding cycle with supercritical CO2, and the one that went through the thermal debinding and sintering steps. The first thing that appears here is that the microwave cycle was not very optimized because there is still a lot of residual porosity inside the sample. However, it was possible to obtain sample, even though they had defects, it was possible to handle them. And also it's possible to see here that the use of the microwave could enable to reduce the grain size of the sample and therefore improve the mechanical properties. So this was more of a proof of concept that the microwave debinding and sintering cycle could be used in combination with the SLA process. However, there is still a lot of improvement to be done on this technique and a lot of optimization on the thermal debinding and sintering cycle, microwave, sorry. So in conclusion, a homemade resin was prepared and enabled to manufacture printable suspension with around 49% of beta-TCP powder, which was a high enough solid load. The light parameter and slice thickness were adapted to the composition of the suspension. The debinding and sintering cycle were built based on the composition of the suspension, and all of that could be applied to the production of complex shape. Also, and provide parts with relative density above 98% and with interesting biological properties. Moreover, alternative routes for the debinding and the sintering step were explored and gave encouraging results for the pursuit of this work. So during my PhD, I also got the chance to valorize a little bit my work. So I wrote an article that is published in Open Ceramics, and I got the chance to participate in different conferences where I presented posters and oral presentation, and I could win some prizes along the way. I would like to thank everybody at the BCRC, firstly, for being there with me during my 3 years of PhD, and also the personnel of the LMCPA that welcomed me here and helped me with my experiments. I would also like to thank the CER group. Without them, I couldn't have done the biological characterization. The Litos company that also admitted me for a week where I was able to use their experiments, the Doc3D Printing members for funding this project, and the Stepan company that provided me with the dispersants. Thank you all for your attention, and I'm here for your question.
Thank you very much for this very elaborate and clear presentation of the years of work you have done. So that means after this we will start the questioning. And the first questions, the first two people that are going to ask the question are the rapporteur. And I would like to start to give the word to Christelle Koen from the University of Toulouse, and you will have about 15 to 20 minutes.